Hello everybody, Root Beer here. We're looking at the 2016 CIMC paper and we are starting part B. So we are on the last three questions, the written questions for the contest. So we need to, as they say, justify or explain our solutions, and marks are awarded for completeness and clarity and style, though I've been in the marking room and I'm never quite sure what they mean by style. I think that probably comes into it more if it's a remarked paper. Anyway, so we need to basically, if we make a claim, we got to justify it. If we say a number, we got to explain where the calculation is. Okay. Question 1. In the grid shown, the distance between adjacent dots in one column and adjacent dots in one row is 1 unit. So this is a nice little lattice of dots. Okay. You can sort of think of these as, think of the Cartesian grid, and just look at the points whose coordinates are both integers. That's a fantastic way to look at these lattices. Okay. Now you can do math without putting any of these sorts of numbers on it. There's a great, there's sort of a wealth there of lattice geometry things, as we can sort of see looking ahead. We got pictures on these dots. But that's, if you need to think about it that way, integer coordinates is just fine. Okay. So, they tell us that the distance is 1 unit. That's fine. We've got 3 pictures here. I imagine we're going to have to be computing some perimeters or areas, but let's take a look. 1A, determine the area of ABC. B, determine the area of DEFGH. Determine the area of JLK. Okay. Now, as an experienced mathematician, when I look here, I notice that each of my vertices, each of the corners of my figures, are actually points on the lattice. They are dots. Okay, otherwise, I mean, if J were slightly askew, you wouldn't be able to tell how far away is J. So they kind of have to put the dots on here. Now, they're just asking us to compute area. And depending where you are in your understanding of mathematics, how much mathematics you read, how much mathematics you've looked up, or you know, what exactly you've been taught, there's actually a really, really fast way to do this question by a result called Pics Theorem. Okay? So I'm just going to very briefly talk about Pics Theorem. I'm not going to prove it or anything like that, because I'm not going to be using it. I'm going to show you how you would do this if you didn't know Pics Theorem. But since it's a thing that I know I've taught to grade 9 and 10s, which are the age group here, I just thought I would address it very briefly here. What to do if you ran into a question like this and you knew Pics Theorem, or what to do if you ran into a question that can be very easily solved with some particular circle geometry, angle-y sort of thing, or, you know, Stewart's theorem or something like that. What do you do when you happen to know you know this really nice mathematical result? It's somewhat advanced or outside the school system, but you're presented with a question and you could bash it quite easily with a hammer. It's sort of a two-liner, as we say, you know, two-line proof. You state this, you get our result. So what do you do when you got that? So that's what I'm going to address right here. Now, Pics Theorem, very nice. I'll see if I can remember it. If you imagine, still got the purple from the last question. If you imagine a lattice, Pics Theorem is exactly about lattices. It doesn't have to be the nice square lattice that we see here. It can really just be any lattice. And I think that's going to be good enough. And you draw a figure, and it can be any figure as long as the corners of the particular shape are on the lattice points, the dots. As long as the corners are on the dots, and you're made with straight lines, and it doesn't cross, and it doesn't have any holes in it. You can extend Pics Theorem to talk about holes and stuff like that, and probably crossing as well. Then there's a nice quick way to figure out the area. So you can calculate the area in terms of the number of points on the interior. Okay, so we call those I. So here I would be 4. And the number of points that lie on the boundary. So I'm going to change this one ever so slightly, just so I have other points that lie on the boundary other than just the corners. So we'll do that. So corners, so all the corners are counted but also this point right here. He's not a corner, but he is on one of the lines that are the boundary of my polygon. So we have half the number of boundary points. So in this case, 1, 2, 3, 4, 5, 6, 7. And then you subtract 1. Okay? So the area of this particular figure would be 4 plus 3.5 minus 1. So that's 7.5 minus 1, 6.5. And if you want to, you can actually see this. You can break it up into, so there's 2 boxes with area 2. There's a third box. So that's 1, 2, 3, 4. And then here's a half right here. And then both of these two guys, these two triangles right here, they can be taken and glued together, and they give you the remaining 2. So 1, 2, 3, 4, 5, 6, and then a half. So it really is 6.5. So this is a nice result called Pics Theorem. Maybe I'll make a video about it, because it's neat, but it sort of lies outside the education system. And depending on how far in the future you're watching this, maybe I've already made a video on Pics Theorem. I have some ideas for little topics I want to do. But I want to have a nice wealth of contest papers first. Anyway, so what was I saying? Well, what do you do with this question if you know Pics Theorem? Do you just say, I know Pics Theorem, here's the answer to A, here's the answer to B, here's the answer to C, I'm done? Okay, does that count? Or do I need to prove Pics Theorem? Okay. And it's such a weird question because it rarely comes up. And usually if you're in the position that you know the really advanced thing that's going to work on it, you either already know another way to do the question, or you already know, or you've already encountered this sort of situation or seen other people encounter it and said, well, how do you write that on a contest? So my advice is this. Let's say it's question B1 like it is. B1, not going to be that hard whether or not you do it the Pics Theorem way or the intended way. But B1, we have to actually show our work. And saying, I know Pics Theorem, is that really showing your work? I mean, yeah, you know it. The people who are marking it know it, or, they'll go ask the chief marker and then they'll know it. But, what do you do? In my opinion, for B1, I would say do it the other way. Because you're probably smart enough to know the other way. And I'm going to go through the other way. But if it's something like B3, and you can't think of an easier way to do it, it's just, it's screaming at you in the face, use cyclic quadrilaterals, or whatever the concept is. Use Pics Theorem, and you can't think of an easier way to do it. What I would suggest you do is you fully state the result and its name. Okay? Pics Theorem says, if you have a lattice polygon, you can compute the area of the lattice polygon by this, 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 and this is your calculation. You fully state the result and give it its proper name. Don't say, this is true that the area is this. You say, this is Pics Theorem, or whatever name of whatever thing you heard. This is Heron's formula, this is Stewart's theorem, whatever it is. And you fully state it, and then proceed to apply it, and apply it quite clearly. Okay? I've got this quantity, I counted this, so I plugged these numbers into Pics Theorem as full sentences. Okay? So that's if you think you've got a really advanced thing that's going to smash the question to bits really quickly and you can't think of an easier way to do it. Okay? Because remember, in B part, we get our marks for our work. Okay? With B1, it's probably not going to take you that much more time to do the question the way they want you to do it than to use Pics Theorem. B3, if you can't see the really convoluted way and you happen to know that second-year university result that gets you there, use it. State it clearly. If you're going to use calculus, and you shouldn't be using calculus on these papers, but if you're going to use calculus, you better state your result and you better make sure it's correct. Because if you say, oh, I'm going to use calculus to solve this, and it's a grade 9 level contest, and you don't state everything clearly, they're going to say, he doesn't know what he's talking about. He said calculus, he said some things, and he thinks he's got the right answer. But does his work check out? If there's even that tiniest bit of error, people are going to chuck it out. Okay? So that's my advice. So for this one, if you knew Pics Theorem, great. If you wanted to fully state it and then say how it applies, you'll probably get full marks. But you could probably also just do it the way they intend you to do it, which is the way I'm going to try and do. Well, I don't know if it's the way they intend you to do it, but it's the way I'm going to do it now, which has no Pics theorem. We're just going to compute the areas and things like that. Okay. So, rant over. I don't want to dwell on this concept because I do actually want to do B1. Most of you probably aren't here to talk about Pics theorem. You're here to talk about B1. So, we've got 1A. Determine the area of ABC. I'll also do a Pics theorem calculation to show you that our answer and Pics theorem match up. But we've got this ABC. It's a triangle. It's a right-angled triangle. And we can copy it into our notebook. And we've got A up here. And then B is 2 spaces down. And C is, I actually have no idea. I think it was 3 spaces over. Yeah. So C is over here, and then we do have a single dot in here, and then another dot outside, 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 outside. So here's ABC. Well, what I would do is I would say ABC is clearly right angle, and right angled. Okay, and I would either label the picture or state AB is equal to 2, BC is equal to 3. The area of this triangle is going to be 1/2 base times height. So that's going to be 1/2 3 times 2, or an area of 3. Okay, and there's my answer. I've explained it. It's right angled. I've labeled a diagram. Said this is my base, this is my height, there we go. Now, how would this work with Pics theorem? Well, after having fully stated Pics theorem, and I'll leave it to you to look that up. I'm not going to write one of those down now, because I don't want to waste more time on Pics theorem. But how would it work? Well, we've got 1 point on the interior, and we've got 1, 2, 3, 4, 5, 6 points on the boundary. So that's going to be 1 plus 3 minus 1, or 3. So Pics theorem got the same answer here. But you'll notice Pics theorem, if you knew this formula, would just be a single line. And it'll actually be a single line for all the other questions. So that's how I would do A. Now B part. We got a slightly bigger figure. We got D, and then I think 3 spaces down it was E. Let's double check. Yeah, 3 spaces down, and then 2 spaces down, and 3 spaces over was F. And 2 spaces over from F was G. And then we go all the way back up. I'll draw in all my lattice points. There we go, H. Alright. So here's our figure. And, I've done questions like these in the past. View the figure not so much with its dots for a moment, but just what is this shape? What does it look like? More importantly, what is it missing? It's missing a tiny little corner, and that turns it into a rectangle. So DFGH is a rectangle minus a triangle. A right-angled triangle, nonetheless. In fact, if you compare, it's going to be the exact same size as the ABC that you just figured out. Okay? So that's some useful stuff. So what are the dimensions of this rectangle? Well, now we can compute that. There's 3 and 2 here, and the dimensions of the rectangle, there's 3 up here and 2 here, so it's actually a square. So the area is going to be 5 squared minus 1/2 base times height. So 25 minus, well, we just calculated that, it's 3, 22. So what should we do? Well, we should explain, hey, I can realize that this shape is just a square minus the right angle triangle. I'll compute the area of the square. I'll compute the area of the triangle. The difference has got to be the remaining area, the DEFGH area. So you could add sentences as you need for that. I'd say what we've got here is fairly clear. Maybe add a sentence or two or something, like a summary sentence, like DEFGH has an area of 22, or put a box around this, that sort of thing. But the key part of this question is recognizing DEFGH as a square or rectangle with a little chunk bitten out of it. Okay. Out of curiosity, how would we do this one with Pics Theorem? Well, we count up the interiors. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Plus 1/2 boundary points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Minus 1, so this is 15 plus 8 minus 1, or 23 minus 1, also 22. So that's Pics Theorem, but again, I recommend you don't do this even if you know Pics Theorem. Okay, and we'll flip the page because we need probably a little more space for that final one. There we go. So let's go back and take a look here. Determine the area of JKL. So it's a triangle here. But it's not quite as nice as ABC. We don't have a clear base or a clear height. Notice if you moved A over 1 dot, you'd still have the base of 3 for BC, and it would be quite clear what the height is. But here we don't have a base or a height sitting around. Well, even though it's a very basic triangle, what we can still do is sort of the same thing we saw with DEFGH. DEFGH was a rectangle with a smaller triangle bitten out of it. Well, we can recognize JKL as a big rectangle with not 1, but 3 smaller triangles bitten out of it. So I know it goes J down to K. I think it's also over 2 and then up by 5 or something like that. Over 2 and then up 1, 2, 3, 4, 5. So up 1, 2, 3, 4, 5 to L. I'm just adding these all in. Because we're going to need them in just a second. Okay, so there's JKL. Do they actually... So it narrowly misses everything, so I'm going to have to see if I can draw it narrowly missing everything. Okay. So something we could say is we can see that JKL is equal to, and then we could say something like the big blue rectangle. Or if you wanted to, you could give it names like A, B, C. So we could is equal to the area of A, B, C, L, and then minus some smaller triangles. This one. You could say minus the 3 red triangles, or if you didn't bring color, giving these things names. So minus the areas of AJL, JBK, and KCL. And if you want to, add the triangle symbol in front of them. Each of these are right-angled. So we go over 2 here, we go over 3 here, up 2 here, 1, 2, 3 here, 3, and then this one is 5, 5 here. So ABCL has an area of 5 squared, and then I would probably, AJL, it's going to be 3 and 5, so he's going to be 1/2, 3 times 5. JBK is going to have an area, well, we've seen this one a couple times, a half 2 times 3. And finally, KCL is going to be a half 2 times 5. So the area here is 5, the area here is 25, this one is 3, and this one is 7.5, or 15 halves, however you want to write it. So the area of triangle JKL is 25 minus 3 minus 5 minus a half 15, or 7.5. The 3 and the 5 is 8, so that's going to be 25 minus 8 is 17, minus 7.5 should be 9.5. Okay, you can put a box around it. We've got our therefore statement. We've also, more clearly than the last 2 times, actually explained the calculation we're making. Okay, now just for funsies, I'll Pics Theorem it for the last time, and then we are going to be done this question. We've got 3 points on the boundary. And so since we have an odd number of points on the boundary, that's where the half is going to come in. Minus 1, and then how many interior points? 1, 2, 3, 4, 5, 6, 7, there's 8 hidden in here, and 9. So this is 9 plus 1.5 minus 1, or 9.5. So we've indirectly shown how effective Pics Theorem is at answering these questions, but again, B1, it didn't take us that long to do it the long way around. When in doubt, just because these contests are time sensitive, I guess use the faster method, but as I say, clearly word it. Okay, Pics Theorem is the following. This is what a lattice polygon is. This is what a boundary point is. This is an interior point. If we count these and perform this calculation, we get the area. That is Pics Theorem. Okay, if I were marking it, I would require all of that before I gave full marks to this equation equals 3, this equation equals 22, this equation equals 9.5. Okay, I know Pics Theorem. You may know Pics Theorem, but you have to explain that you know it and really know it. Okay, as opposed to just saying, by Pythagoras, this happens. I would not accept by Pics Theorem, this equals this. By Pics Theorem, this equals this. No. If you're going to use something really advanced to turn it into a 1, 2, 3 line proof, state the result you're using. Okay. But that does it for B1. I think I've talked more about Pics Theorem than I actually talked about the question here. But there you go. So really it boiled down to some right angle triangles and recognizing odd shapes, odd polygons as regular, like normal. I don't mean regular the other way. I mean like just normal everyday polygons subtracted or added to each other. Okay. So that's B1. In the next video, we're going to take a look at B2, another written question, and we'll see how it goes from there. So thanks for watching, and join me for more of the CIMC coming up.